Quantum computers have a dirty secret hiding behind all the hype. The tiniest vibration, a stray flicker of heat, even a rogue particle from outer space, can destroy a calculation before it finishes. For decades, this fragility has been the single biggest wall between quantum computing as a laboratory curiosity and quantum computing as a tool that can actually change the world. And in October 2025, NVIDIA quietly announced the piece of infrastructure built specifically to tear that wall down. The technology is called NVQLink. And if you care even a little about where artificial intelligence, science, and computing are heading over the next decade, this is one of those moments worth stopping and understanding properly. It was unveiled on stage in Washington, D.C., and standing behind the announcement was NVIDIA's CEO, Jensen Huang, who made a claim bold enough to stop people in their tracks. He said that in the near future, every single NVIDIA GPU scientific supercomputer would be hybrid, tightly coupled with quantum processors, expanding what computing itself is even capable of. He went further, calling NVQLink the Rosetta Stone connecting quantum and classical supercomputers, a phrase meant to capture the idea of uniting two very different kinds of machines into a single coherent system, marking the onset of what he described as the quantum GPU computing era. To understand why that framing matters, you have to understand the fragility problem properly, because it explains almost everything about why NVQLink exists in the first place. Qubits, the basic building blocks of quantum information, are extraordinarily sensitive. Unlike the transistors inside a classical computer chip, which can reliably hold a 1 or a 0 for years without any special intervention, qubits exist in delicate quantum states that can be knocked out of alignment by almost anything happening around them. Heat is an enemy. Electromagnetic interference is an enemy. Even the physical vibration of a nearby air conditioning unit can be enough to introduce error into a running quantum calculation. This isn't some minor engineering inconvenience that clever software can quietly work around. It is the central, defining challenge of building a quantum computer that can do anything genuinely useful. To fight that fragility, quantum systems need constant correction. They need something watching over them in real time, catching errors the instant they appear, decoding exactly what went wrong, and feeding a fix back into the system before the noise spirals out of control and destroys the calculation entirely. This process is called quantum error correction, and it is punishingly difficult because it has to happen on a timescale of microseconds, millionths of a second. A classical computer trying to babysit a quantum processor through this process needs to be fast. It needs to be genuinely powerful. And critically, it needs to sit close, in a networking sense, to the quantum hardware it's watching over. Here's the catch that quietly held the entire industry back for years. There was no clean, standardized, high-performance way to connect a quantum processor to a powerful classical supercomputer for this kind of real-time correction work. Every research group, every hardware company, every national laboratory experimenting with quantum computers had to essentially invent its own bespoke wiring between its qubits and whatever classical compute happened to be available. Some of it worked reasonably well inside isolated experiments. None of it was built to scale. None of it created a common language that let a quantum processor built by one company talk cleanly to a supercomputer built by an entirely different vendor. It was a fragmented, ad hoc mess, and it was quietly throttling progress across the entire field. This is exactly the gap NVIDIA walked into with NVQLink. At its core, NVQLink is an open system architecture, a kind of universal adapter that connects quantum processing units, often shortened to QPUs, directly to GPU-powered supercomputers. Think of it less as a single product and more as a shared set of rules and hardware standards that the whole quantum computing industry can build around. Instead of every company reinventing the wiring from scratch, NVQLink gives them a common, high-speed, low-latency bridge that simply works, regardless of whether the quantum hardware underneath is built from superconducting circuits, trapped ions, neutral atoms, photonics, or silicon spin qubits. And this wasn't a solo NVIDIA project cooked up quietly in a lab and unveiled as a surprise. It was from the very beginning a coalition effort. 17 different quantum hardware companies contributed to shaping NVQLink. 5 separate companies that build the control systems responsible for actually operating quantum processors chipped in their expertise. And 9 United States national laboratories, institutions with decades of hands-on experience pushing the boundaries of high-performance computing, lent their guidance to the design. We're talking about heavyweight names here: Brookhaven, Fermilab, Lawrence Berkeley, Los Alamos, MIT Lincoln Laboratory, Oak Ridge, Pacific Northwest, and Sandia, alongside additional support from the National Institute of Standards and Technology. When that many serious, independent institutions choose to align behind one shared architecture rather than compete with rival standards, it signals something important. It signals that the industry recognized this wiring bottleneck as an existential threat to progress, and collectively decided the smartest move was to solve it once together rather than over and over in isolation. The involvement of the Department of Energy adds another layer of weight to this story. The DOE oversees several of the national laboratories that helped shape NVQLink, and the agency has publicly framed this collaboration as part of a much bigger national strategy, an effort to make sure the United States holds onto its leadership position in high-performance computing as the world edges toward a genuinely hybrid quantum classical future. This isn't simply a corporate product launch. It's being treated, at least in part, as a piece of national scientific infrastructure, something that could shape which countries lead the coming decades of computational science. So how does NVQLink actually work under the hood? Let's break down the architecture in plain terms, because the engineering here is genuinely elegant. The system is built around a handful of core components working together. First, there's what NVIDIA calls the real-time host, a GPU-accelerated server capable of running the kind of high-speed parallel code that modern AI supercomputers are famous for. Second, there's the quantum system controller, sometimes shortened to QSC, the hardware responsible for the delicate, moment-to-moment job of coherently controlling and reading out a quantum processor. Third, connecting these two pieces is the real-time network, a purpose-built data pathway engineered specifically to move information between the classical host and the quantum controller with almost no delay. And finally, tying it all together programmatically is the cudaq-realtime API, a runtime software library that lets developers write code referencing CPUs, GPUs, and FPGAs across both the classical host and the quantum controller, and coordinating work between them almost as if they were one unified machine rather than two separate systems bolted awkwardly together. What makes this particularly clever is that NVIDIA didn't try to force everyone into using its own proprietary software stack exclusively. Developers are free to build on top of the NVQLink architecture using tools other than NVIDIA's own CUDA-Q platform, as long as whatever system they build supports the cudaq-realtime API standard. That's an important detail because it turns NVQLink from a walled garden into something closer to a shared protocol, the kind of foundational layer an entire ecosystem can build on top of without being locked into a single vendor's world forever. Now let's talk numbers, because the technical specifications here are genuinely impressive and worth understanding in real terms. NVQLink is capable of moving data between quantum control systems and GPU servers at speeds up to 400 gigabits per second. Independent benchmarking has measured round-trip latency, meaning the time it takes for a signal to travel from the quantum controller to the GPU and back again with a useful response at a maximum of roughly 96 microseconds. To put that in perspective, that's a few millionths of a second, fast enough to comfortably fit inside the incredibly tight timing windows required for real-time quantum error correction. And here's the part that should genuinely surprise you. NVIDIA achieved these numbers using RDMA over converged Ethernet, commercially available 400 gigabit networking hardware. This is not some exotic, laboratory-only, science fiction interconnect. It's essentially the same high-speed networking fabric that large-scale AI training clusters already use every single day to train massive language models, which means any data center or research facility already running serious GPU workloads has most of the physical infrastructure needed to plug into NVQLink without a complete rebuild from the ground up. That's a massive practical advantage because it dramatically lowers the barrier to adoption across the industry. It helps to have a simple mental picture for why this matters so much. Think about how a modern AI data center works. Thousands of GPUs sit connected together over extremely fast networking, constantly exchanging data as they train massive models, and the entire system only works because that networking is fast enough and reliable enough to keep every chip synchronized. Now, imagine trying to add a completely different, far more delicate kind of processor into that mix, one that can lose its entire computational state if a signal arrives even a few microseconds late. That's essentially the challenge NVQLink was built to solve. It's not just about raw speed, it's about precision timing, about guaranteeing that a correction signal generated by a GPU actually reaches a struggling qubit before the error it's meant to fix has already spiraled into something unrecoverable. Get that timing wrong, and the quantum processor effectively falls apart mid-calculation. Get it right, consistently at scale, and you start to unlock quantum systems that can run for meaningfully longer stretches of productive computation. The hardware ecosystem responded to this almost immediately. Dell validated several of its server platforms, including models known as the XE7745, the XE96680, the R775, and the R770 as certified real-time host systems, successfully reproducing NVQLink's sub-4 microsecond latencies in independent testing. That kind of third-party validation matters enormously in enterprise and research computing because it tells procurement teams and lab directors that this isn't just a marketing claim from NVIDIA's own press release, it's a reproducible, measurable, real-world capability. It's also worth pausing here to appreciate just how varied the underlying quantum hardware actually is, because that variety is exactly why an open, shared standard like NVQLink is such a big deal. Different companies are racing forward with fundamentally different approaches to building a qubit. Some rely on superconducting circuits, cooled to temperatures colder than deep space. Others use trapped ions, individual charged atoms, suspended and controlled with lasers. Some systems use neutral atoms arranged in careful optical patterns. Others work with photonic qubits, encoding information directly into particles of light. Still others are pursuing silicon spin qubits, built using manufacturing techniques borrowed from the conventional chip industry. Each of these approaches has wildly different physical requirements, different noise characteristics, and different control electronics. Before NVQLink, that diversity meant a fragmented landscape where progress made connecting one type of quantum hardware to classical compute rarely transferred cleanly to another. NVQLink's entire value proposition rests on cutting straight across that diversity, giving every one of these fundamentally different quantum technologies the same fast, standardized on-ramp to GPU-accelerated classical computing, regardless of what physics is happening inside the processor itself. Let's fast forward a few months, because the story didn't stop at the initial October 2025 unveiling. At NVIDIA's GTC conference in 2026, the company took the next major step by making NVQLink publicly available through a brand new application programming interface called cudaq-realtime, released as part of the CUDA-Q 0.14 software update. This was the moment NVQLink moved from an architectural announcement and a set of demonstrations into something developers could actually start building with directly. The cudaq-realtime library gives programmers a runtime API specifically designed for handling microsecond latency callbacks between GPUs and quantum controllers, essentially the software plumbing that makes the tight feedback loop of real-time quantum error correction possible in practice, not just in theory. At that same GTC event, NVIDIA also detailed 3 distinct execution modes for how developers can actually use the link depending on their performance needs. There's a default 3-kernel dispatch mode, which uses GPU visible ring buffers to handle incoming data packets in a straightforward, flexible way. There's a more advanced unified kernel mode, which folds receiving, dispatching, and transmitting data into a single persistent process running on the GPU, squeezing out every last drop of latency for teams that need the absolute fastest possible response times. And there's a lightweight transport-only forwarding mode, essentially an echo function used purely for baseline network benchmarking, letting engineers measure raw round-trip performance before layering more complex logic on top. What's genuinely remarkable is just how quickly the broader quantum computing ecosystem moved to adopt this new capability once it became available. Qblocks, a leading provider of quantum control stacks based in the Netherlands, integrated cudaq-realtime to build a direct, high-speed bridge between NVIDIA's accelerated computing platform and Oxford Quantum Circuit's full-stack quantum computers. This kind of integration specifically targets a notorious bottleneck in variational quantum algorithms, and where fast, high-throughput feedback between classical and quantum systems is absolutely essential for getting useful results. Quantum Machines, another major player in quantum control systems, folded cudaq-realtime directly into what they call their open acceleration stack. qctrl, a company specializing in quantum control and calibration software, reported something genuinely striking after integrating NVQLink into their QPAC deployment: a 50 times reduction in classical processing overhead, and a 5 times speed-up in overall wall clock time for their workloads. Those aren't marginal incremental improvements. Those are the kinds of performance gains that can be the difference between a quantum experiment that's practically useful and one that remains a laboratory curiosity. Elsewhere, SDT deployed what's being described as the first tightly coupled hybrid quantum classical data center in South Korea, using their own controller technology alongside NVQLink to connect an anion computing quantum processor directly to NVIDIA GPUs. DRAC, a company working on silicon spin qubit technology, is using NVQLink to link its processors with accelerated computing for calibration, auto-tuning, and benchmarking work. Atom Computing successfully integrated NVQLink into its proprietary control system stack. IQM, a Finnish quantum hardware company, teamed up with Zurich Instruments to build a real-time quantum error correction demonstrator, combining a 20-qubit IQM processor with Zurich Instruments' control system and NVQLink's real-time networking layer. And Quantinuum, one of the most advanced players in the trapped ion quantum computing space, demonstrated genuinely demanding real-time error correction work, using correlated decoding techniques on their system. That relationship with Quantinuum deserves a closer look because it stretches beyond a single demonstration into a deeper, ongoing research partnership. At the NVIDIA Accelerated Quantum Computing Research Center, sometimes shortened to NVAQC, An NVIDIA GB200 NVL72 supercomputer, one of the company's most powerful GPU systems, has been paired directly with Quantinuum's Helios quantum computer. Together, this hybrid system is being used to push forward what's called generative quantum AI, or GenQ AI for short. One striking early achievement from this collaboration is something called the ADAPT GQE framework, a transformer-based approach that uses generative AI techniques to efficiently design quantum circuits capable of preparing what's known as the ground state of a chemical system on a quantum computer. In plainer language, that means using AI to help figure out the most efficient quantum instructions for simulating how molecules actually behave at their most stable, lowest energy configuration. Work with serious implications for chemistry, material science, and drug discovery. And speaking of scientific applications, that's really where all of this technical wiring starts to matter to people outside the quantum computing industry itself. Sinica and Kipu Quantum used NVIDIA's CUDA-Q platform to achieve a 43-qubit state vector simulation running across more than 2,000 NVIDIA GPUs. An enormous simulation task that pushes classical hardware to its limits while helping researchers understand quantum behavior before ever touching real quantum hardware. Research institutions, including University College London, the Technical University of Munich, and IQM used CUDA-Q to accelerate simulations in biomolecular research and quantum error correction. Inflection applied similar technology to cancer biomarker discovery work, and researchers at the University of Edinburgh reported speedups of up to 900 times in their quantum error correction workflows after adopting these accelerated tools. These aren't abstract engineering wins buried in a technical paper somewhere. They represent real progress toward using quantum augmented computing to tackle problems in medicine, chemistry, and materials science that classical computers alone genuinely struggle with. The geographic reach of this effort has expanded well beyond the United States, too. Scientific supercomputing centers across Asia have adopted NVQLink to integrate NVIDIA's Grace Blackwell computing platform with quantum processors, including Japan's Global Research and Development Center for Business by Quantum AI Technology, operating under the National Institute of Advanced Industrial Science and Technology. This tells you that NVQLink isn't being treated as a niche American research project. It's rapidly becoming something closer to a genuinely international standard for how quantum and classical computing infrastructure connect to one another. So why does all of this actually matter? Beyond the impressive list of partnerships and benchmark numbers, here's the bigger picture worth holding on to. Quantum computing has spent decades living almost entirely in research papers and small-scale laboratory demonstrations, tantalizing but stubbornly impractical for solving real-world problems at any meaningful scale. The core reason for that gap has never really been a lack of clever quantum algorithms. It's been the brutal difficulty of keeping fragile qubits stable long enough and correcting their errors fast enough to do genuinely useful, sustained computation. NVQLink attacks that exact problem head-on by giving the industry a fast, standardized, and now commercially validated way to connect quantum hardware with the kind of powerful, GPU-driven classical compute needed to keep those fragile qubits corrected and coherent in real time. If this architecture continues to scale the way its early adoption numbers suggest it might, the implications ripple outward in several directions at once. For quantum hardware companies, it lowers the engineering burden of building their own custom classical interconnects from scratch, freeing up their teams to focus more energy on improving the quantum processors themselves rather than reinventing networking infrastructure that other companies have already solved. For national laboratories and research institutions, it creates a shared, interoperable foundation that makes collaboration across different quantum hardware platforms dramatically easier than it's ever been before. For industries watching from the sidelines, pharmaceuticals, materials science, finance, logistics, and beyond, it represents a meaningful step toward the kind of hybrid quantum classical computing that could eventually tackle optimization and simulation problems that remain firmly out of reach for classical supercomputers, acting alone no matter how large or powerful they get. Of course, it's worth staying grounded here too. NVQLink solves a crucial piece of infrastructure, the wiring problem, the communication bottleneck between quantum and classical systems. It does not, by itself, solve every remaining challenge in quantum computing. Qubit counts still need to grow. Error rates still need to fall further. Fault-tolerant quantum computing, the kind capable of running long, complex, commercially meaningful calculations without being overwhelmed by noise, remains an enormous engineering challenge that the entire industry is still working through step by step. What NVQLink does is remove one of the most stubborn practical obstacles standing in the way of that progress, the lack of a fast, standardized, real-time bridge between the classical machinery watching over quantum systems and the fragile quantum processors themselves. There's also a broader strategic story unfolding here worth sitting with for a moment. NVIDIA built its dominance in the artificial intelligence boom by becoming the essential infrastructure layer underneath nearly every major AI breakthrough of the last several years, the company whose chips and software quietly power the vast majority of serious machine learning work happening around the world. With NVQLink, the company is making a clear, deliberate bet that quantum computing's future will not exist as a completely separate, isolated technology running parallel to classical and AI computing, but rather as a tightly integrated extension of the same accelerated computing infrastructure NVIDIA has already spent years building and refining. It's also worth putting NVIDIA's move here into competitive context, because the company is not operating in a vacuum. Other major players in computing have their own visions for how quantum and classical systems should eventually work together. IBM has spent years building out its own quantum hardware roadmap alongside classical integration efforts through its Qiskit software ecosystem, pursuing a somewhat more vertically integrated approach, where IBM builds much of the hardware and software stack itself. Google has continued advancing its own superconducting quantum processors and error correction research through its quantum AI division, chasing many of the same fault tolerance milestones from a different technical direction. What sets NVIDIA's approach apart is the deliberate choice to stay out of the business of building quantum processors altogether. Instead of competing with quantum hardware companies, NVIDIA positioned itself as the connective tissue underneath all of them, the accelerated computing layer that any quantum hardware maker, regardless of their underlying technology or corporate rivalry with each other, can plug into. That's a strategic echo of exactly how NVIDIA rose to dominance in artificial intelligence in the first place, not by trying to build every AI application itself, but by making sure nearly every AI application in the world runs on NVIDIA's chips and software underneath. There's an economic dimension to this story too, one that's easy to overlook amid all the technical detail. Building and operating quantum hardware remains extraordinarily expensive, and until recently, much of that expense came with no clear path to a return on investment beyond publishing research papers. By giving quantum hardware companies a fast, standardized, commercially validated way to plug into existing GPU infrastructure, NVQLink effectively lowers the cost and risk of scaling quantum systems towards something closer to commercial usefulness. A startup building a novel qubit modality no longer needs to independently solve the classical interconnect problem from scratch, burning through funding on infrastructure work that has nothing to do with their actual quantum physics innovation. They can instead adopt an already validated, already benchmarked architecture, and redirect their limited engineering resources toward the parts of the problem that are genuinely unique to their hardware. That kind of shared infrastructure tends to accelerate an entire industry, the same way standardized shipping containers once accelerated global trade far more than any single faster ship ever could, simply by removing friction at the connection points between different systems. That's the real significance behind this announcement and behind everything that's followed it since October 2025. It's not simply that NVIDIA built a faster cable connecting two different kinds of computers. It's that an entire coalition spanning 17 quantum hardware companies, 5 control system providers, 9 national laboratories, a federal energy department, and a growing list of research institutions and industrial partners all converged around a shared belief that the era of quantum computing as an isolated standalone curiosity is quietly coming to an end, and the era of quantum computing as one integrated piece of a much larger hybrid computational future has already begun. Whether you work in technology, in science, in finance, or simply follow this space out of curiosity about where computing is heading next, this is a development worth watching closely, because the infrastructure decisions being made right now in research labs and data centers around the world are quietly setting the terms for what problems become solvable and what breakthroughs become possible over the next decade of scientific discovery. Think back to where the story started, that quiet warning about fragile qubits and rogue particles capable of derailing an entire calculation. In the months since NVQLink was first announced, that warning has turned into working silicon, validated servers, published latency benchmarks, and a rapidly growing list of research institutions and hardware companies building real systems on top of it. That's a remarkably fast journey from a stated problem to functioning infrastructure, and it's a strong signal that this wasn't hype dressed up as innovation. It was a genuine attempt to solve one of the most persistent bottlenecks standing between quantum computing's enormous theoretical promise and its practical, everyday reality. Nobody can say with certainty exactly how quickly fault-tolerant, commercially useful quantum computing will arrive, or which breakthroughs will ultimately prove decisive along the way. But NVIDIA, along with an unusually broad and serious coalition of partners across industry, academia, and government, has now built and deployed one of the clearest, fastest, most standardized bridges yet between the quantum systems of tomorrow and the powerful classical computing infrastructure already running the world today. And bridges, once they're built and people start crossing them in large numbers, have a way of quietly reshaping everything on both sides of them.